Dr. Ranjani Partha is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer architecture. We have been looking at various aspects of a computer system. Of late we have been looking at the input-output system. With respect to input-output system, we have already looked at interrupts, we have looked at the DMA mechanism, and also we have seen the different interface circuits. We have looked at the serial interface, parallel interface circuits and so on. So what we will be looking at in today's lecture is a little bit on some I/O standards. We will also look at some I/O devices and some trends with respect to I/O devices. So when we talk of standard I/O interfaces, there are three widely used bus standards that we normally hear about. Okay. One is the PCI, which is called as the Peripheral Component Interconnect Bus. Second is the SCSI bus or the SCSI, Small Computer Systems Interface Bus, and then we have the USB, the Universal Serial Bus. I am sure that most of you would have heard of the USB, the Universal Serial Bus, even if you have not really heard of the PCI and the SCSI. The PCI and SCSI actually are pretty much internal to the system. So you might not have heard of PCI and SCSI, but you definitely have heard of the USB bus, because this is something which we use to connect up external devices. So if we look at the PCI bus, the Peripheral Component Interconnect Bus as it is called, this is a system level bus. So it is a low cost processor independent internal bus. So processor independent in the sense that different processes could be connected to this particular bus, and you can have different devices connected to this bus so that the processor can talk to the different devices. It is a synchronous system bus which works at about 33 megahertz or 66 megahertz. There are two versions available. And then we have the SCSI bus, which is a small computer systems interface. This is typically used to connect disks and so on. Disks, and sometimes you have SCSI based printers also available. So this bus is a little different from the PCI bus in the sense that this provides you external connectivity. The PCI is an internal system bus. The SCSI is an external bus, so you can have a SCSI cable up to about 25 meters. So it can kind of connect out of the system, and you can have different SCSI based devices which are located outside of your PC, and you can have the SCSI bus connecting up those devices. You have special SCSI cables which are used for that purpose. We have different standards there. SCSI was the original standard. Then we have SCSI 2, SCSI 3 and so on. Based on the standard, the data rates at which you are able to do data transfer, the number of devices that you can connect, all these things would vary. We are not going to the details of those, but just that you need to know that these kind of standards exist. In this case, when we are using the SCSI bus, the devices connected are not part of the processor address space, which is why I said this is an external bus. When you look at the PCI, the buses, the different devices which are connected as part of the PCI are normally part of the processor's address space. So here the addressing of the SCSI system itself is considered to be different from the system's address space or the processor's address space. So that is about these two buses, the PCI bus and the SCSI bus. The Universal Serial Bus or the USB ports that we are familiar with, right? The USB ports essentially are ports through which you are able to connecting to the USB bus. What is interesting about the USB bus is that it is a serial bus. The PCI and SCSI are all parallel buses, in the sense that you have number of bits being transferred simultaneously, whereas here this is a serial bus. And the idea of using a serial bus essentially is that you will be able to achieve higher speeds of data transfer with little interference between the different bits that happen actually in a parallel bus. So that is the reason why people have gone in for a serial bus and a complete standard which is based on the serial bus, which is the USB. So when we talk of USB, these are terms that we come across: a low speed USB or a full speed USB or a high speed USB. Low speed typically works at about 1.5 megabits per second, that is the data transfer rate. Full speed is about 12 megabit per second, and high speed is about 480 megabit per second and so on. The way the devices are connected on a universal serial bus is by means of a tree like structure, so that you can have actually a large number of devices connected to a single USB bus. Okay, that is the these are the three standard buses that we see. Now if you look at how these buses typically appear within a system, this picture should give you some idea of how the different devices get actually connected. So let us start with the processor. The processor and the main memory are typically connected by means of a processor bus, and then we normally have something called a bridge. Okay, a bridge is you can look at it as some interface circuitry which is used to connect the processor to the rest of the system. So, normally the bridge itself is divided into a north bridge and a south bridge sometimes, and you have the north bridge being used to connect to the main memory and the south bridge used to connect to the different I/O devices. So, we have a bridge here. This bridge on one side connects to the processor bus, on the other side connects to the PCI bus. So, you can see that the PCI bus is the standard that is being used over here, and to this PCI bus you can have additional memory connected, you can have different controllers that are connected. The configuration that we are looking at here is that we have a SCSI controller that is connected to this PCI bus and also a USB controller connected to the PCI bus. So, the SCSI controller, remember the SCSI is used to connect other external devices. You can use this to talk to a disk, or you can use it to talk to a CD-ROM and so on. So, we have the SCSI bus. So, through SCSI bus we are able to connect to the disk controller and the CD-ROM controller, and through the disk controller and the CD-ROM controller different disks and a CD-ROM is connected. So, you can see the kind of a hierarchical structure that is used over here. So, you have the PCI bus to which the SCSI controller is connected, and the SCSI controller is connected to the SCSI bus, and through the SCSI bus we have different disks different devices connected through their respective controllers. So, disk 1 and disk 2 are connected by means of disk controller to the SCSI bus. CD-ROM is connected by means of its CD-ROM controller to the SCSI bus. Okay, this is how the SCSI bus would be connected. Similarly, you can see we have a USB controller here which connects to the PCI bus, and to the USB controller you can have different USB devices connected. It can be a game console or it can be a keyboard, video, all these can be connected by means of the USB controller. Okay. Other than this, of course, we are showing that there is a Ethernet interface and so on. There is also an ISA interface that we are showing over here. This is one of the older standards that were used on PCs to connect up various devices. You can also have an ISA interface connected to the PCI bus, and therefore you can still provide some kind of a compatibility with older devices that would work only with an ISA interface. If you open up your PC or whatever and see, this is typically what you will see on the motherboard. This is again another view of a typical x86 PCIO system. So, I was talking to you about a north bridge and a south bridge, right. So, this is typically what it will look like. So, here we are looking at an Intel Xeon processor. The bus that connects the processor to the memory controller is normally referred to as the front side bus. FSB is the term that they normally use, front side bus. You can see that it works at about 1.33 gigahertz and can do about 10.5 gigabyte per second data transfer. So, these are the kind of data rates that are supported on these fast systems that we have. So, then you have this north bridge. To this north bridge you have the main memory connected. So, the north bridge normally is used to connect to the main memory. South bridge is used to connect to the IO. So, we call this as the memory controller hub, and this we call as the IO controller hub. Okay, that is the south bridge. So, the south bridge you can see will be connected to different IO devices. You have a disk controller that may be connected, different disks can be connected, keyboard, mouse, USB, okay, and then other PCI extension buses can be connected to it. You can have a parallel ATA, which is again another standard that is used to connect CDs and DVDs. So, this can be connected over here and so on. So, this is another typical configuration that we would see within a system. Now, we will take a look at different storage devices and the features of these storage devices. So, we will start with the disk storage, which is basically a non-volatile rotating magnetic storage. If we look at the inside of a disk, what you will actually see is it is actually a series of disks which are arranged together. You can see that each of this is a platter. Okay, there will be a number of such platters which actually form your complete disk. Now, on each platter data is stored in concentric circles that you can see, which are called as tracks. Okay, these are different tracks. So, you have different tracks which are there on a particular platter, and within each track you can see that data is divided into sectors. That is, you split up the entire track into smaller units called sectors. So, on a track you have multiple sectors, and the different tracks of platter, that is track number 1 of platter 0, track number 1 of platter 2, 3 and so on, that together is considered as a cylinder. Okay, these are some of the terms that we use when we talk about disk storage. We talk about tracks, cylinders and sectors. So, track is, it refers to what is, there are different tracks. So, we talk about track 0, track 1, track 2 and so on, and then within each track you have multiple sectors, okay, and groups of tracks together form a cylinder. Okay, this is a term that we normally use. I mean, these are the terms that are used to refer to a particular block of storage which is there within a disk. So, normally we will be referring to a particular sector which is situated on a particular track, okay, or on a particular cylinder to say. Okay, that is how we will identify this. So, if you look at what is actually stored, data is stored in terms of these sectors. Okay, so each, you can look at a sector as a particular block of storage, and so each sector will have the following information. It will have a sector ID to identify which sector we are referring to, and then the actual data, which is about 512 bytes or 4096 bytes. In fact, now we have 4096 byte data storage on the sectors, and then there will also be an error correcting code or an ECC that is stored along with the data. Now, the purpose of storing error correcting code is basically to hide any defects that may be there and recording errors. Whenever there is a defect, for instance, the error correcting code will be used to identify that there is an error and correct it if possible. Okay, that is the purpose of an error correcting code. Okay. Then in addition to the error correcting code, the ECC information, there will also be some synchronization fields and gaps which are there for every sector. Now, this is in order to make sure that your data is recorded correctly and that you are able to read it back correctly and so on. Okay. So, this is the information that will go into a sector, and then when you access a sector, okay, you will find that typically what will happen is that if you look at this picture, these disks are rotating at a particular speed, right. So, and there will be a head which is located, which is kind of located on top of this on top of each of these disks for platters as such. And so, what actually needs to happen is that the area which comes in contact with the head, that is the one from where you will actually be able to read the data. So, what will happen is that the sector will rotate and come under the head. So, that is what needs to happen. Okay. So, if you look at how the data will be read, you will see that you first have to seek to a particular track. So, you can see that there are different tracks, right. So, you need to go to a particular track first. So, seek is the first operation that is done. So, we have some delay for doing the seek itself, it is called as a seek time. Seek time is the time taken for the head to move to a particular track. Note that there are different tracks. If your head is at the outer track, okay, for it to go to the inner track, there is some time that will take for the head to actually move, it is a mechanical movement. Okay, so, it will take some time. So, that is called as the seek time. The seek time is the time taken to move the heads. And then we talk about a rotational latency, which is the time that it takes for the disk to rotate, so that that particular sector comes under the head. So, remember the head is, let us say the head is somewhere over here. So, the sector that we want to read has to come to this position. So, the disk has to rotate, okay, for it to come over here. That time that it takes for it to rotate and come under the head, that is called as the rotational latency. Once it comes under the head, now the data transfer can take place. So, you read the data and then you transfer the data, okay, and then it goes through the controller. Remember that all our disks are sent through a controller. So, a controller overhead would also be there for doing the data transfer. Okay. All this is assuming that you are ready to do the data transfer. But if there are already other accesses which are pending, some IO access taking place on the disk, then there will be a delay because you will be waiting in a queue before the access can be completed. Okay. So, if you look at the total time that is taken for accessing the disk, therefore, it has all these components. There will be a queuing delay if other accesses are pending. If there are no accesses pending, then of course, we will start with the seek delay. Seek is to move to a particular track position, and then rotational latency for the sector to come under the head, and then the data transfer time, and then any controller overhead time that may be there. Okay. So, all these things put together will constitute the time taken to access a particular data from the disk. We will take a short break and then come and look at an example of how the disk access time can be calculated. Welcome back after the break. So, we were just looking at how the disk access time can be calculated. So, there are these components that we talked about: queuing delay, seek time, rotational latency, data transfer time, and the controller overhead. So, we will take an example and see how these times actually add up together. So, let us consider an example where I have a 512 byte sector. It rotates at 15,000 RPM rotations per minute. 4 milliseconds is the average seek time. Remember that we are looking at average seek time here because depending on where the disk is currently, right, it may take different amounts of time for it to rotate and come to the correct position. So, we look at the average seek time, and then we are assuming that we have a data transfer rate of 100 megabytes per second, and then there is a 0.2 millisecond controller overhead. Okay. Let us assume an idle disk, which means that there are no accesses pending, so there is no queuing delay. Okay. So, minus queuing delay, let us look at how much time it will take for the access to be completed. All right. So, let us start first with the seek time, right, that is the first component that we looked at, right. So, we have a 4 millisecond average seek time. So, we take that component first, plus we said there will be a rotational latency. Now, rotational latency is the time taken for the disk to rotate so that the position comes under the head. So, now that we have 15,000 RPM, that will come to about 15,000 by 60 to look at it in terms of number of rotations per second, okay. And then average rotational latency, that is it may not take a full round. For instance, if it is nearby, it will come back immediately. If it is at the other end, you will have to wait for a complete rotation. On an average, therefore, we can say that it takes about half a rotation, the time taken for half a rotation we can say is the rotational latency. So, half a rotation it will take, so 1 by half divided by 15,000 by 60, that comes to approximately about 2 milliseconds, that is equal to 2 milliseconds as latency time. So, rotational latency is 2 milliseconds, 4 milliseconds is the seek time. Next thing that we need to look at is the data transfer time. Now, the data transfer time is from a sector we can read 512 bytes, and once you read the 512 bytes, it is transferred at a rate of 100 megabytes per second. So, 512 bytes at a rate of 100 megabytes per second, right, 512 divided by 100 megabyte per second, that comes to about 0.005 milliseconds as the transfer time. Now, we said that there is a 0.2 millisecond controller overhead, so we add the 0.2 milliseconds as well. So, if you add up all these together, it comes to about 6.2 milliseconds. Okay, so you can see that the average read time will be 6.2 milliseconds for a single sector. If the actual average seek time, now we said the average seek time is 4 milliseconds, right? The actual seek time, so let us say was only 1 millisecond, then the average read time would come to about 3.2 milliseconds. Okay, so you can see that there are different components over here, and you can see that the seek time happens to be the largest of these. 4 milliseconds for seek time, 2 milliseconds for rotational latency, 0.005 milliseconds for the transfer time, and 0.2 millisecond controller delay. If you are able to reduce the seek time, you will be able to reduce the overall disk access time. So, when we look at performance of disk, therefore, many times our concentration is on the average seek time. So, manufacturers for instance quote the average seek time, okay, which is based on all possible seeks. Okay. But when you actually try to lower the seek time, it can be done with the help of looking at some locality issues and the operating system scheduling for the disk. Okay. So, OS scheduling plus locality normally will lead to smaller actual average seek times. Okay. So, you will look at how the disk scheduling is done by the OS when you study about OS. Of course, other than this we have smart disk controllers which also try to allocate physical sectors on the disk in such a manner that your overall access time becomes faster. So, typically what the smart disk controllers will do is they will present a logical sector interface to the host and take care of the actual physical interface through the different buses, this SCSI bus for instance that we saw. Okay. Another thing that the disk drives will also do is they also include caches. So, caches we have seen always helps us to improve performance, right. So, similarly there are caches present in the disk drives and you prefetch sectors in anticipation of access. So, put it into the cache, prefetch the sectors so that you can avoid the seek and rotational delay for every access. So, while some access is taking place, you already transferred some of the data over here, it is some kind of a pipelined access that you can look at. Okay. So, by providing for caches, you can try to improve the disk performance. That is what many disk controllers today do. The next device that is very commonly used is the flash storage device. So, if you look at the flash storage device, again it is another non-volatile semiconductor storage. It is about 100 times to 1000 times faster than a disk and it is smaller, lower power and more robust. The only thing is of course it is more expensive, more dollars per GB between disk and DRAM. Okay, that is the kind of thing that we have. So, this is just a picture of what is there inside your USB stick. Okay, you can see that there is some kind of a controller device and there is a flash device that is sitting inside your USB disk. If we look at different types of flash, okay, these are the terms that we will come across. We talk about NOR flash and NAND flash. NOR flash when we talk about, here a bit cell is like a NOR gate and this will allow for random read write access and this is normally used for instruction memory in embedded systems. A NAND flash when we talk about, here a bit cell works like a NAND gate, okay, and with NAND flash you can have denser data storage, that is more number of bits per area, okay, but the access is normally done block at a time. Okay, it is not a bit by bit access, but you do a block by block access, block at a time access that is used. So, this normally gives us a cheaper storage per gigabyte and this is the one that is normally used in our USB keys, media storage and so on. Okay. One of the problem with the flash devices is that the flash bits wear out after about thousands of accesses. So, which is why your USB drive can wear out after some time. Okay. So, it will wear out after thousands of accesses. So, it is not suitable therefore for a direct RAM or a disk replacement. Of course, now we are coming up with other flash technologies which are also coming in as replacements for RAM and disk and so on. Okay. But to tackle the wear problem that we have, there is something called wear leveling that is used. That is, there may be some areas of your disk which are used often, so they will wear out soon. So what you do is you will remap data to less used blocks. So that is something which the flash controller would normally do in order to make sure that you are able to tackle this kind of a wear out problem that can happen in flash drives. Another common storage media that we have is our optical storage. Optical storage, in fact CDs, DVDs, all of them have a similar mechanism that is used for storing data. What happens in optical storage is that data is stored in the form of what are called as bits and lands. Okay. So land is whenever I have, for instance, when you have zeros, they are stored as a particular as a land level, and you have bits which are used for storing ones and so on. Okay. So whenever you have a transition, for instance, you have a bit, and when there is another transition, you come back to a land and so on. So these are the kind of different ways in which data can be stored. The idea basically is that when you have a bit, it's like a small dip that is there in the coating that you have. So you have a laser which kind of incident on the surface that you have here, and it gets reflected back. Now depending on whether you have a land or a pit, the amount of data that gets reflected becomes different. Okay. So based on that you identify whether it's a land or a pit, and based on that you identify whether it is a 0 stored there or a 1 that is stored over there. So this is the simple mechanism that is used for optical storage. And again, depending on the kind of storage device that we actually have, we have different layers and different coatings which are used over here. Okay. So there is a lacquer layer and then an aluminum layer, and then there is normally a polycarbonate layer which is a clear plastic which is used for protecting the inner layers that we have. Okay. So data is stored basically by carving out these pits on the different surfaces that are available. On optical discs, data is normally stored along a spiral. Okay. It is a spiral kind of shape that is used for storing the data. On magnetic disc we saw that it is more like a concentric circles. Here it is more of a spiral kind of a data storage that we have. And CDs normally store only one layer of data, and it is normally read from inside to outside. DVDs you can have normally you have two layers of data, and so that one layer we read from inside to outside, and then the second layer is read back to inside, from outside back to inside. With DVDs you can also have double sided DVDs, which means you would have actually 4 layers of data that can be stored, which is why DVDs give you a higher rate of or denser data storage. Okay. So instead, in fact, this is some interesting information that you can look at. Suppose we were to lift the data track off a single layer of a DVD and stretch it out into a straight line. It can be almost up to 7.5 miles long, which means if you have a double sided double layer DVD, that means 7.5 into 4. Okay, so you will have about 30 miles of data. So that is the amount of data that we are actually storing on the DVDs. So that is a kind of some interesting information for you to look at. Okay. So in general, when we look at in I/O system performance, one of the factors which is very important is dependability. Okay, so dependability is what we look at. That is, we want the storage devices to store data for a long period of time, and we want it to store it correctly. Okay, so dependability is an important aspect that we look at when we talk about I/O system performance. Okay. Other performance measures of course are latency, which is the response time, throughput, which is the bandwidth. And for desktops and embedded systems, we are mainly interested in response time and diversity of devices. For servers, we are mainly interested in throughput and expandability of devices. Okay, these are the factors that we look at when we look at I/O system performance. Okay. So when we talk of dependability, what is it that we are looking at? We know that a failure can occur, and when a failure occurs, there will be some service interruption, okay, some deviation from the specified service, and then when we restore it back, we get back to the service being delivered. When do we say we have a fault? It is a failure of a component, and it may or may not lead to system failure. Okay, so that is something that we need to look at. So dependability is identifying that there is a fault, then there may be some kind of a time that is taken up for repairing the fault, and then we come back to. So the cycle of dependability is something that we need to understand. Okay. So if we look at dependability measures, therefore, these are terms that we talk about. We talk about something called mean time to failure. This is a measure of reliability. What is mean time to failure? That is the average time that it takes before a machine can fail. So if your mean time to failure is large, that means your system is very reliable. Okay, that is, it takes a long time to fail, which means that it is reliable. Okay, that is what we say. Another term that we talk about is mean time to repair. Okay, this is MTTR, which is the time it takes for the repair to be done. So mean time between failures therefore will be the sum of mean time to failure plus mean time to repair. Okay, that is how long it takes before a failure occurs, and then when a failure occurs, how long it takes for that repair to be done. So MTTF plus MTTR will give you the mean time between failures. Okay. So, availability we can say is MTTF divided by MTTF plus MTTR. Okay. So, this is what availability is. So, if I want to increase availability, that is what our goal always is, right. How will I improve availability? I can improve availability by increasing MTTF, that is mean time to failure, and by decreasing the MTTR. Okay. That is what we normally do. Okay. This is done, MTTF increase is done by means of fault avoidance, fault tolerance techniques and so on, by providing duplicate devices, duplicate disks and so on, and MTTR reduction is done with the help of improved tools which will be able to allow us to do the diagnosis and repair faster. Okay. So, this is what we have. So, to improve reliability, one of the things which is done is a redundant array of inexpensive disks. A technique called RAID is used. Okay, technology in fact called RAID is used. So, redundant array of inexpensive disks. So, what we do here is we use multiple smaller disks rather than one large disk. So, the effect is that you can access these disks in parallel, therefore, you get improved performance, and since we have these extra disks, we can also do it for doing redundant data storage, therefore, we can come up with fault tolerant storage systems. Okay. So, this is something which is used in many high performance disk systems. So, when we talk of RAID, in fact, we talk about different RAID levels. There are different types of redundancy that can be provided with the help of these RAID systems. One is RAID 0, in fact, we talk about different levels, level 0, 1, 2, 3 and so on. Level 0 is no redundancy, okay, but helps to improve performance because you have multiple disks. In RAID 1 and 2, what we do is we mirror the data, that is, if there are n disks, another n disk replicate the same data. So, you will write data to both disks, to both the data disk and the mirror disk. If one disk fails, you can always read from the mirror. Okay, that gives you one kind of a flexibility. RAID 2, we use what are called as error correcting codes. So, you will have n disks and you have some error correcting disks. Okay, so 10 plus 4 for instance. So, data is split at bit level across the n disks and the error correcting the ECC is stored in the E disks. Okay, this is a little complex, so it is normally not used in practice. The other option that we have is a bit interleaved parity. All of us know about the parity mechanism. So, we store parity information on the redundant disk. This is also not really used widely. One that is widely used is a mechanism called a distributed parity. Okay. So, what we do here is we use n plus 1 disks. Okay. There is n disks for storing the data and 1 disk which is used for storing the parity information. Okay. So, what we do in this RAID 5 is that you store your data spread across different disks 0, 1, 2, 3 and so on, and then the parity of these disks, right, of this information P0 is stored on one of these disks. Okay. We do not have one disk which is dedicated for storing parity, instead we store parity on different disks. Okay. So, for instance, for the first level of data 0, 1, 2, 3 parity is stored over here. For the next 4, 5, 6, 7 parity is stored in this disk P1. For the next set of data 8, 9, 10, 11 parity is stored over here and so on. That is, if we take for instance 5 disks altogether, 4 of them are storing some information, the 5th disk stores the parity. That 5th disk parity information is not one fixed parity device but stored across multiple devices. With this, what happens is that you can reconstruct the information if one disk fails, and even if one disk fails, it is not that entire information is lost, because the parity information is stored across disks, the reconstruction can be done in a better manner. So, this is called as a distributed parity mechanism which is used on RAID. So, to summarize what we have looked at today, we have looked at different bus standards, we looked at PCI, SCSI and the USB bus, and we looked at some storage devices, how data is stored on disks and so on, both magnetic disks and optical disks. We also looked at the RAID, which is a redundant array of inexpensive disks, which is used to improve performance and reliability. Okay. A set of questions to look at what we have done today. Question number 1, what are the functions of PCI and SCSI? Question number 2, list the factors that determine the access time for a magnetic disk. Question number 3, how is data stored on optical disks? Question number 4, what is the idea behind RAID? Question number 5, how does RAID level 5 work? Question number 6, what is meant by MTTF? Thank you.